Okay, so I have done a lot of work on the Earth and planets in the solar system, and I sort of consider my research to be dealing with dirt, air, and sometimes green slimy stuff. And 25 years ago, astronomers really were not interested in this kind of thing because you can't have clean physics equations, particularly for the green slimy stuff. But now it's become very relevant, and in particular with the fact that life on Earth makes gases that go into an atmosphere, and we can detect these gases and therefore infer life on a planet. So what I'm going to talk about are three things. One is how the gases in the Earth's atmosphere come, most of them, with the exception of the noble gases, come from life. And in principle, if we can detect something like that, we can find life on another planet. Then a framework for assessing biosignatures in general. What we want to be able to do is to look at a spectrum and say, okay, there's a 66% to 100% chance of life based on our data. So, it's likely. Or there's a 33 to 66%, so this would be, for example, somewhat inconclusive. And then I'm going to talk about Proxima Centauri B and M-dwarf planets at the end. So look at the right here. On the right, we see the iconic image of our planet as a dot, a single pixel in the dark vastness of space from Voyager 1 and then later from Cassini with the moon. This is a pale blue dot. And what I want to emphasize is that even something as basic as the color of our planet from a distance is biological. And the reason it's biological is because it comes from these contributions: Rayleigh scattering from a clear oxidizing atmosphere, ozone that absorbs in the yellow-orange and takes out that component, and basically clouds, which then makes it the pale color. And so it's related fundamentally to the composition of the atmosphere, which over on this side is oxygen and nitrogen, and things like lightning and other processes can make nitrogen oxides. And if you photolize NO2, you can make oxygen atoms that combine with oxygen molecules to make ozone, which has been lost here. That should be an O3. And then if you photolize that, you get excited oxygen. And because our planet is wet, that can react with an H2O and make a couple of two OH radicals. And the two OH radicals, these things with unpaired electrons, roam around the atmosphere and get rid of all the muck, things like CH4, ammonia, and so on. They oxidize it, and it rains out, gone. So we have a nice transparent atmosphere that does a lot of Rayleigh scattering and looks blue. And where does that come from? It comes from life, producing that oxygen, also modulating the nitrogen through a biological nitrogen cycle. So something as basic as the color of our planet is modulated by life. Also, incidentally, the Earth is the sunniest planetary surface with thick air in the solar system because of this. You can go one step deeper, and you can look at the individual gases, as was done with the Galileo flyby of the Earth in 1990. And in this spectrum, you can see things that are biological, such as methane, produced by microbes, or nitrous oxide, N2O, produced by microbes, or oxygen, produced by life, or its product, ozone. But if you looked at a spectrum like this, which was perhaps degraded and you had less information, what in particular is distinctive to show that there's life? So there's an old idea, and it's still current, about looking for compounds in the atmosphere that are incompatible on a long-term basis. In other words, they should react with each other. And the fact that you see them shows that there are strong fluxes of these gases going into the air. A pair that's very important, oxygen and methane, which I've drawn here. And the oxygen methane should react together to produce carbon dioxide and water, like that. So the fact that we see plenty of oxygen in the atmosphere and also methane means that there's something producing the methane, which I've illustrated with the cow. Of course, it's the microbes inside the gut, and also the grass and the tree here producing the oxygen. So this is what we call chemical disequilibrium or thermodynamic disequilibrium. And if you calculate it for the solar system atmospheres, which is something I did recently with a couple of students, you find that the Earth has the largest thermodynamic disequilibrium in the solar system. However, it's a question of degree. There's always free energy coming into a planetary atmosphere through solar radiation, stellar radiation, that can create some disequilibrium by dissociating molecules. So for example, in the thin atmosphere of Mars of carbon dioxide, that's easily dissociated and makes oxygen and carbon monoxide, some levels of those gases in the atmosphere. And so there's an abiotic disequilibrium. But it's not as big as the disequilibrium of the Earth, which is actually dominated by nitrogen, oxygen, and water, which want to be nitric acid, and also with a contribution from oxygen and methane. But there's another complication here, which is that the Earth's atmosphere, the composition has changed in time. So what you're going to see in Earth history, if you look back through time, would not be the same as that Galileo flyby spectrum. And so this is a sketch of the evolution of gases through time of the Earth. And in fact, prior to about 2.4 billion years ago, there are vanishingly low levels of oxygen. And then later on, oxygen rose and then rose again to higher levels. And there have also been histories of methane and carbon dioxide. So what this means is that the spectrum of the Earth has changed over time from an oxygen-rich one to a slightly less oxygen-rich one, if you go back 2 billion years, to one with methane and an absence of oxygen. So what about the disequilibrium of the early Earth? So that's something we've calculated also, but not published. And actually, this disequilibrium gets less as you go back in time, because oxygen is a very energetic molecule for redox reactions. But as you go back in time, there's still disequilibrium. It's just between the two kind of end states on the redox ladder of carbon, oxidized carbon at one end and hydrogenated carbon at the other end. That would be a disequilibrium that exists on the early Earth 3 billion years ago that you could look for as a sign of life if there's a lot of methane. And in general, this idea has to work at some level, because if the one thing I'm certain about life on other planets is that it's going to have some kind of metabolism. And in the periodic table and the products in the periodic table that you can get from it, the energetic reactions are all redox reactions. Now, people have mentioned, Omawa mentioned the idea of false positives, that you might see some abiotic process that mimics the production of what otherwise is a biogenic gas, for example, oxygen. So we have to become exoplanet pathologists, because these situations are pathological cases where there are particular characteristic parameters where you'd get that abiotic false positive. So you need to think about that. Can we diagnose that pathology? If not, can we say that we've found life? So this is a table, and in recent years, there's been a little bit of a cottage industry in oxygen false positives, particularly around M-dwarf stars. And on the left are those ideas, and on the right, in the red, is some diagnostic context that could tell you that it's a false positive. And in the blue are some grumbles about why these ideas, these hypothetical ideas, might be wrong. So consider those to be like, the grumbles of the two old men on the Muppet Show saying, well, I don't think so really about this idea or that idea. So you could have a dry planet with CO2 and it could photolyze. You can have an extreme Mars, which would build up oxygen, but you would know that it's dry. You wouldn't see much water vapor. You'd see a lot of carbon monoxide. There's this idea, which is fine, that planets around M-dwarfs during the early phases of the M-dwarf would have been subject to a lot of irradiation and could have entered a runaway greenhouse effect and maybe built up a lot of oxygen. But oxygen chemically will thwart the hydrogen escape, and these models currently don't have that chemistry, and were it included, that problem may in fact go away. Oxygen, by the way, is undetectable on Venus, which is our one example in the solar system that we think had a runaway greenhouse effect. If there was a lot of oxygen buildup, you could detect it. It's more difficult, but with an O4 dimer. M stars have relatively low near UV radiation, and this can limit ozone destruction, so you might see some ozone as a false positive, but these models have sinks on the oxygen that are quite low, and so it depends upon these assumptions of the model. Were it truly like the early Earth, for example, this probably wouldn't happen. And then there's the idea of atmospheres that simply don't have non-condensable gases, like nitrogen might be almost very CO2 rich, H2O rich atmospheres, which could also possibly build up oxygen. But whether these are cosmochemically plausible or not, given that nitrogen is quite abundant and delivered with carbon and water, is unclear. I still think, because of all of those reasons, that oxygen is the best bet. We can detect it at relatively small concentrations in the visible spectrum, and even smaller concentrations through ozone in the UV or the thermal infrared. And the other gases that are biogenic all have issues. So methane can be produced abiotically or can be primordial, as it is on the giant planets or on Titan. Ammonia, well, that's what we see when we look at Jupiter. We see ammonia clouds at the top. And nitrous oxide, very low levels, difficult to detect. And then there are a suite of other biogenic gases, like the sulfur gases, that are very low levels, and it's hard to conceive that they would necessarily be detectable. So oxygen, I still believe, is the best bet. But if you want to assess these biosignatures, you're going to have to do it in a way that assesses the likelihood of the data coming from life or coming from an abiotic system. This is Bayesian statistics, where you're going to have to take observational astronomy, which is your data for spectra, and also your context, everything you know about the stellar system. And you're going to have to try and model that with a planet that maybe has a biosphere or doesn't have a biosphere, and that will contribute to your likelihoods of the data given the context and life, or the data given the context and no life. And in Bayesian statistics, you also use prior probabilities. Now, when I first showed this diagram to an astronomer, they said, oh, how are we going to do this? We don't know priors. I said, but you use priors all the time. It's called the habitable zone, where your estimate of life in that habitable zone goes up. So it has to be formalized in this way to eventually end up with what we want, which is a probability that the hypothesis of life on an exoplanet is true given the observational data and context. So what about Proxima Centauri B? Well, we know that early on it was not in the habitable zone. That's just what we see now. That was close, that was farther away. So it could be Venus-like if it had run away and turned into a Venus, but it could also have had a sacrificial evaporated envelope of hydrogen and then a secondary atmosphere. So it could be Earth-like, could be Mars-like, could be Io-like. And this is an animation of some simulations we've done of how the planets at the top there on the right, which have big envelopes, can become rocky by sacrificing their envelopes due to irradiation. And as the irradiation drops, that becomes less likely, and it can explain this 1.5, 1.6, actually we get 1.7 Earth radii transition to rocky bodies. So how could there be life on Proxima Centauri B? Well, it has to originate, and if we're looking for oxygen, oxygenic photosynthesis has to evolve. Unfortunately, currently, there's no accepted theory for either of how these things happened on the Earth exactly. There's another interesting topic, which is that photosynthesis relies on electronic transitions. And as we know from basic physics, once you get out into the infrared, you tend to excite vibrations and rotations, and the electronic transitions don't happen. The peak of Proxima Centauri is 0.95 microns. It's kind of maybe doable. But as you get to the smaller, really late M dwarfs, maybe it isn't. There's also a time for oxygen to build up. So you can have oxygen production, but it just gets eaten up by all the things in the environment that oxygen can react with. And in general, bigger planets could be a bigger sink for oxygen. It depends on a whole host of issues. The bottom line is there's much uncertainty. And so exoplanetary biology, I think, is a great empirical opportunity. But there is some good news. Because there's less near UV coming from an M dwarf, let's suppose you just had something Earth-like, that Proxima Centauri B was an Earth-like atmosphere, and it had an Earth-like flux of methane into its atmosphere. Well, actually, that means that there's less of that detergent I talked about earlier on, the OH radical, because there's slower ozone production of excited oxygen, less production of the OH radical, and methane, for the same biological flux, would build up to much higher levels, like 800 ppm. So it's actually more biogenic than the Earth would be if you looked at its spectrum. So I conclude that extraterrestrials with big telescopes could have detected life on Earth probably since 3.5 billion years ago if they were clever. Firstly, from oxygen for the last 2 billion years of Earth history, and then from other disequilibria between methane and CO2 for early Earth. Deducing a probability of life's present from future exo-Earth data needs to consider these likelihood models, and there's a lot of work to be done in that three-part diagram that I showed you regarding the priors and likelihoods. And Proxima B and other M-dwarf planets, there are many unknowns. We have to take the Kepler mission approach, which is you look to see what's in the cosmos optimistically, and you'll probably find some strange things, but you'll also find some things that you expect. But the principles that I've outlined here about how to find life from biogenic gases will apply. Thank you. Questions? There's a couple down here if somebody has the microphone. Nobody has the microphone? Okay, just go ahead.
You focused justifiably so on life as we know it.
Yes.
But potentially one could find the signatures of life as we don't know it. In other words, there would be complete disequilibrium in some other types of gases. Can you venture into that realm, or is that completely out of the scope in the near future?
Well, I've never heard anybody give me a good explanation of how we find life as we don't know it. That's because of the don't know bit. What we do know is that there's a limited toolkit, the periodic table, and there's only certain energetic reactions you can have with molecules that you can make from the periodic table. And it's a good question, because is the biochemistry of Earth somehow a natural outcome of the kind of geochemistry that we expect to have on a rocky planet? So a rocky planet, we know that it's going to have magnesium and silicon oxygen-rich rocks, because these are the peaks in the cosmochemical abundance, which relates to nucleosynthesis. So there is some commonality in geochemistry that very likely leads to some commonality, I believe, in the biochemistry. And the kind of metabolisms you have, because of the energetics, will tend to produce certain products, like methane would be an obvious one. If you found, there's one thing I didn't mention, which is if you find a lot of food and no one is eating it, that could also be an anti-biosignature. And I've done this experiment myself with students, where I have leftover candy from Halloween, and I leave it out, and if nobody eats it, well, they've gone to a party and I wasn't invited. But so there's a way to also, so carbon monoxide is a good example of that, which should be eaten by microbes, and then hydrogen with carbon dioxide, that's a good redox couple that should be eaten by methanogens. But life as we don't know it, I think you have to frame it in terms of what we know, which is, that's the simplest thing to look at least at first. If we find something weird, we'll figure it out after the fact. Lisa.
Really interesting, David. Thank you. I was curious about, in your paper, you showed in Disequilibrium, right?
Yes.
That when you don't take into account that Earth has an ocean and an atmosphere, it doesn't stand out that much. However, when you take these two into account, it does. And the conclusion in the paper you had was that you hadn't modeled any other system, with an ocean and non-ocean to cross-compare. Do you have any, now with the Earth through geological time that you're working on, do you see the similar standing out to disequilibrium going back in time because you use it as a two-component, ocean and air, versus just as one component, that's the overall disequilibrium? Or does it actually narrow down when you go back in time?
Well, there's two answers to your question, or two relevant parts. One is that, yes, to do the full disequilibrium calculation, you have to take into account that the fluid envelope includes water on the Earth. And the thermodynamic contribution from just oxygen and methane is not that big, because there's not that much methane, only 1.8 parts per million in this air in this room, unless somebody brought a pet cow into the back. But there's a kinetics. So that I didn't talk about kinetics. The fact that that couple exists methane is destroyed on a 10-year timescale instantly, geologically. That means a big flux of methane to sustain that. And so what you could do with an exoplanet is, if you have enough information, is start figuring out the kinetics and say, okay, we need this flux to sustain that molecule. But it becomes a question of degree. Could that be produced abiotically or biotically? So that's the additional information that we're also looking at. But generalizing kinetics for biogenic gas is a little tricky, so we're still thinking about it.